I'm going to talk about surface temperature measurements using infrared radiometers. If you have any questions while I'm talking, feel free to raise your hand and ask, and I'll do my best to address it. I have lots of slides, unlike Bruce, so we're going to shift technologies just a little bit. But surface temperature can be a very important variable in lots of environmental applications, and I'm going to talk about it more in relation to plants today, but bear in mind that you can use infrared technology to measure soil surface temperatures, snow surface temperatures, roadways if you're interested in road conditions, for example. And the three key components to an infrared radiometer are listed here. You have to have a radiation detector, you have to have an internal temperature sensor, and then you have to have a housing to contain the two and be rugged so that it's stable in changing environmental conditions. And so the basic operation is as follows. We all know from physics that all objects that have a temperature above absolute zero emit infrared radiation. So whatever you point the sensor at is going to be emitting infrared radiation towards the sensor. In this case, it's a plant canopy. And the sensor itself has a temperature above absolute zero, so it's also going to be emitting radiation back out, so to speak. And the signal that's actually measured by the radiation detector inside the radiometer is proportional on this difference between the absorbed radiation that's coming from the surface that you're pointing it at and the emitted radiation from the detector itself. And those signals can be quite small. An example of a common infrared radiometer outputs 60 microvolts, that's 0.06 millivolts per degree C difference between the target that you're looking at and the temperature of the sensor itself. So what this means is if you're making an analog measurement of this, you're measuring the voltage directly, you need a high resolution voltmeter in order to measure that small signal and to get an accurate number. So I've listed here about 1 microvolt is required. You have to have a high-end data logger or voltmeter to do this. So when the absorbed radiation, the amount of radiation coming in, is less than the amount of radiation going out, then the radiation balance at the detector itself is negative and you'll get a negative voltage. So the opposite is true. When you have more radiation coming in than what's going out, the radiation balance at the detector is positive and you'll get a positive voltage rather than a negative voltage. And so in addition to needing a voltmeter that can measure small signals in the microvolt range, you also need one that can measure polarity, both positive and negative voltages. Right, and so I mentioned a minute ago that we all remember from physics radiation and temperature are closely linked. All objects with a temperature above absolute zero emit radiation. And the actual equation that quantifies the relationship between the two is called the Stefan-Boltzmann equation, where the energy emitted by an object, in this case it's a plant canopy, is equal to a constant, that's the sigma, times the fourth power of the absolute temperature. So if we're able to measure the radiation being emitted or the energy being emitted by an object, then we can calculate the temperature. And that's the basic premise for how these infrared sensors work. All right, so another important component of infrared sensors that I didn't actually list on the previous slide is the filter that goes in front of the radiation detector. And so radiation detectors tend to be black bodies, meaning they're good absorbers of all the wavelengths of radiation that are incident on them. Remember, we only want to measure the wavelengths that are related to the temperature of the surface. And so in order to build a radiometer that measures what we're interested in, we have to put a filter in front of it to give us just the wavelengths of radiation that we're interested in. And so a a radiation detector should include a filter that blocks all of the long wave radiation that's outside of what we call the atmospheric window. The atmospheric window is the wavelengths between 8 and 14 micron, and I have a graph here that shows wavelength on the x-axis from 5 to 20 micron, and then transmittance of the atmosphere on the y-axis. The reason we choose 8 to 14 micron is that's the wavelength range that's called the atmospheric window, and it's essentially the wavelengths where the atmosphere is transparent to long wave radiation. Meaning if you point a sensor with a filter that has an 8 to 14 micron window on it, that radiation is going to come through the atmosphere rather than be absorbed or absorbed by the molecules, water vapor and CO2 in the atmosphere. So it's just the wavelengths where the sensor sees through the atmosphere, so to speak. Below 8 micron, there's lots of absorption by water vapor molecules. And above 14 micron, there's lots of absorption by carbon dioxide molecules. So we want to try to measure the surface radiation and not the atmospheric radiation. Therefore, we need a filter that matches the atmospheric window. So just to give you an idea of calibration, I got a couple quick pictures right here. This shows the calibration system that we use at Apogee Instruments to calibrate infrared radiometers. And there's lots of these things commercially available, and we're going to let you play around with some of these handheld devices later. You can get models like this really cheaply at the hardware store, and you point them at the surface that you want, you pull the trigger, and it gives you a temperature. So I just measured the temperature of the floor as 71 Fahrenheit, or if we convert it to Celsius, about 22 Celsius. Right? These are fine, especially for demonstration purposes or just spot checks where high accuracy isn't required. But the main difference between something like this that you can buy at the hardware store for a few dollars and something like this that we manufacture at Apogee Instruments is really the calibration. So something like this, the accuracy is probably 1 to 2 Celsius. Here I'm just showing the sensors. The uncertainty of the calibration is about 0.2 Celsius. So there's an order of magnitude difference between the accuracy of something like this and a research grade instrument. And what you're looking at here is actually a 2-component system, and it's kind of hard to see it, but in the next slide I think it will become clear. There's this cap piece that sits on top of a large piece of aluminum. A piece of aluminum has a big hole in it shaped like a cone, and that's painted flat black. We use that as the black body radiation source that we can fine-tune the temperatures and get specific values of temperature independent of the sensor temperatures themselves. So this cap piece is another block of aluminum that has a bunch of holes in it that you can slide the sensors into and then independently control their temperature. And so what you have is a target, or the black body cone, and a cap that fit together, but we can independently control the temperatures of the two and set this temperature at one value and the sensors at a different value, and derive a whole set of data that allows us to get sensor-specific calibration coefficients for all the radiometers, and we can fine-tune it to 0.2 C uncertainty. So just to give you an idea, there's the actual calibration device with the cap piece pulled off of it, so you can see that it's a black body. I have another one, a small one, that we'll use for a really brief demonstration later. So this is called a Leslie cube, or if you look it up on the internet, sometimes it's called Professor Leslie's cube. I don't know who Professor Leslie is, but I'd like to meet him someday, because it's a really simple and powerful device that we'll use in a few minutes to illustrate the concept of emissivity. But essentially, what you're looking at here and what you're looking at here are similar devices that you can use to calibrate the instruments. All right, so once you have a functional sensor that's calibrated and you take it to the field to make measurements, it's not just a simple matter of putting the sensor out there and recording the temperature that it gives you and accepting that as the true value of surface temperature. We actually have to correct for emissivity effects. So emissivity is just a fraction of black body emittance. So something like this black body cone here, the black body cone that I showed you on the previous slide, they have very high emissivities, well over 0.99, meaning they're almost black bodies. A black body is a perfect emitter, meaning it emits all of the theoretically possible radiation for its temperature. Something that has an emissivity less than 1 is often called a gray body, and it's not a perfect emitter, meaning it emits some fraction of radiation less than it otherwise would if it were a black body. And emissivity is how we quantify the fraction of black body emittance. So if you have a surface with an emissivity of 1, for example, the only radiation coming from the surface that arrives at the sensor is radiation that was emitted by the surface. But if you have a surface less than a surface that's not a black body, so the emissivity is less than 1, here we'll say 0.98, which is a pretty good estimate of emissivity for a plant canopy. That means most of the radiation incident on the detector is coming from the surface of interest, but there's actually a small fraction of radiation coming from the background, and if it's outside, the background is the sky. There'll be a small fraction of radiation incident at the surface that's coming from the sky. The reason why is that the long wave reflection at the surface is 1 minus the emissivity. Right? So if our emissivity is 0.98, that means our reflection of long wave is 0.02. Essentially, you have 98% of your radiation is coming from the plants, which we're trying to measure, and 2% is coming from the background or the sky because it's being reflected off of the plant surface towards the radiometer. And you might ask yourself, why is that a big deal? Well, the plant temperature and sky temperature might not be the same number. If they are the same number, if they're close to the same number, it doesn't matter if you're reflecting a small fraction of the sky radiation towards the sensor. It's similar to the plant canopy temperature. But if the sky temperature is significantly different, it can lead to errors. And so we can correct for this effect with a relatively simple equation. And the equation's listed up here. I won't go through the derivation, but the information that you need to go into the equation to correct for emissivity are the actual measured temperature itself, which we get from the sensor. But then you need some measurement or estimate of the background temperature, and then a measurement or estimate of the surface emissivity. You can see once we have those numbers, they go in the equation here and give us an estimate of the true surface temperature. So just by way of example, on a clear day, the background temperature, and again if we're outdoors, this is the sky, can be really cold in the 8 to 14 wavelength range that the temperature sensor is measuring. So we might measure a surface temperature of a plant canopy of 25 Celsius. A clear day, the sky temperature is negative 40 Celsius. If our plant canopy emissivity is 0.98, our actual surface temperature is at about a degree higher, close to 26 Celsius, than the measured temperature. And so emissivity can have a big impact on temperature measurements, and it's important that we account for it if our application requires accuracy better than a degree Celsius or so. Just to give you another example, on a cloudy day, we'll assume, again, a measured temperature of 25 Celsius, but on a cloudy day, the sky temperature isn't nearly as cold as it is on a clear day. 15 Celsius is a much better estimate of background temperature on a cloudy day. Again, assuming a plant canopy temperature of 0.98, Now the surface temperature, the true surface temperature, is only about 0.2 Celsius above what our sensor gave us. So the emissivity effect will vary with the sky conditions. Clear, sky is cold. Cloudy, the sky is warm. And when we get a break, we'll actually walk outside with some of these low-cost handheld infrared sensors, and you can point them up and measure the temperature of the sky and measure the temperature of the surface and get a feel for how big the differences are. All right, so this table just shows a handful of emissivity values for environmental surfaces and some man-made surfaces, concrete and polished aluminum. So fortunately, most of the surfaces that we're interested in measuring, things like plant leaves and plant canopies, soil, water, they're close to black bodies. Not quite, because none of them have an emissivity of 1. Deep plant canopies that have a lot of leaves can be really close to black bodies, 0.99 in some cases. So the emissivity effect tends to be small in environmental applications, but again, it can be quite important, especially if we have clear sky conditions. And so this just gives you an idea of background temperature. Clear sky will be very cold. Overcast sky will be near air temperature. And this is a simple equation that we derived in Logan, Utah, that you can use to estimate the background temperature or the sky temperature in the 8 to 14 micron range. So you take the air temperature and you add 50 times the fraction of clouds and then subtract 60. So the fraction of clouds is basically what percentage of the hemisphere of sky is cloud cover and what percentage is clear. Right, so let's take a quick break. I'm about maybe halfway through, and we have a break for tea time in just a few minutes. So I'm going to ask if James would go fill our little Leslie cube full of hot water and just show you the emissivity effect in real time. So, yeah, just hot water from the toilet. Just put it in right there. Fill it all the way. And so all we're going to do is I have a couple infrared sensors here, and when we take a break, you're welcome to play around with these. And so it's really simple. Power button, and then you point it at what you want to measure, and it outputs the temperature on the screen in Celsius. So for example, if I point it at the ceiling and we get around 22 Celsius, I point it at the floor, we get about the same number, and that makes sense. The room here is essentially the same temperature, and so the surfaces in the room should be about the same temperature. And so all we're going to do is measure the black body surface of the Leslie cube and then the side of the Leslie cube. And so take a look at these numbers for a second. And I can tell you the side of the Leslie cube, it's polished stainless steel. So polished aluminum has an emissivity of around 0.03 to 0.05. Polished stainless steel will be something similar. I don't know the exact number, but it will be something similar. Now what we're going to do is fill the Leslie cube full of hot water, right? And we know that the black body cone of the Leslie cube is close to a black body, so its emissivity is very near 1. Any ideas what the temperature of the black body cone will be versus the stainless steel side of the Leslie cube if we measure it with one of these sensors? So let's just assume the water temperature will be 50 or 60 Celsius. So what should the black body cone surface temperature be? What's that? Yeah. It should be close to the true temperature because it's a black body, meaning it's emitting the maximum amount of radiation it should emit for that temperature. So what about if we pointed at the side of the Leslie cube and measure the polished aluminum surface? What should the temperature be? What's that? 22. Yeah. Why 22? Yeah. we should see a temperature that's pretty close to the room temperature, because remember, 1 minus the emissivity is the long wave reflectivity. And so let's just assume that the emissivity of this flat side is 0.05. That means 95% of the radiation that we're measuring should be reflected from the room. So we should see something that's maybe about 22 Celsius, because the ceiling and the floor were about 22 when we measured them. So I'll turn it on, and I don't know how well you can see the screen. I'll yell out the numbers for those of you that can't see the screen. If we point it at the black body surface, and the unit actually does some averaging, and so it's up to temperature now. It looks like it's about 38.6 Celsius. Now if I point it at the panel on the side, we're getting about 26 Celsius. So not quite as cold as the 22 that I measured on the floor. And that might be because the emissivity is actually a little bit higher. Maybe the emissivity is like 0.1 or 0.2. So what we're actually doing is getting an average temperature somewhere between the true temperature and the room temperature, because the emissivity is somewhere between 0 and 1, and I don't know exactly what it is.
What would be the result if you move a little back? If you will increase the distance?
Oh, increase the distance, sure. So this is an excellent question, because you're actually jumping ahead in my slides. The next thing I'm going to talk about in my slideshow is the field of view. And so what happens is, if we put it right up next to the black body, we should measure something around 38, and again we're about 38.4. If I slowly start to move it away, in the front row, what's happening? Yeah, it's getting colder and colder. So now we're about probably 12 centimeters, maybe 14 centimeters away, and we're reading 30 instead of 38. And so what's happening is we're moving it further and further from the black body. We're seeing more and more within the footprint that this thing measures. And so now we're starting to move it away, and we're seeing the sides where it's polished aluminum in addition to the black body. And that's determined by the field of view of the sensor. And so I might actually be able to do another demonstration. Let me see if I have a light in my bag.
Mark, let me make a comment while you're getting set up for that.
Okay.
If you look on the internet for manufacturers of infrared radiometers, you will see some manufacturers that sell an instrument with a dial on the back that is allegedly corrects for emissivity. And they say this is a terrific feature. Our instrument's more accurate because we dial in emissivity. What they do is take the reading and multiply it by the emissivity.
Actually, they divide by the emissivity.
Or divide.
Right.
But it often makes the measurement worse instead of better, because they're not including the reflected radiation that Mark's talking about. So, boy, does that confuse a lot of people. They act like it's just a simple dial, you can just correct for this, and that drives people that know what they're doing crazy, because it confuses the issue. You can't just take a dial and correct for emissivity.
Good point, Bruce. So if you have infrared radiometers that have a dial on them that allow you to tune it to the emissivity of the surface, I would strongly recommend that you set that dial to 1 so that it doesn't make that correction. Actually, it will make the correction. It'll take the measurement and it'll divide it by 1 so you get the actual measurement. And then use the equation that I gave you on the previous slide to make the emissivity correction the right way. All right, so if there's no more questions about emissivity, yeah, go ahead.
Sorry, we've got real problems with emissivity down in Antarctica because our moss temperature's in the full sun and it can get up to 20 degrees Celsius, and the air temperature is obviously much colder than that. And so if we use infrared sensors down there, we're finding a low degree of accuracy. And also the mosses, the emissivity can change according to their wet, dry, underwater, frozen, whatever.
Right.
Is there any quick solution for correcting for emissivity if the emissivity is changing over time?
I think the answer to that is you have to actually characterize the emissivity. You need to know what it is with, within whatever degrees of uncertainty you're comfortable with in order to use the equation that I've shown here. So there are ways to measure the emissivity, and if you want, I can give you some direction with regards to papers in the literature that will describe how to measure emissivity. But yeah, in order to use the equation to correct for emissivity, you have to have a pretty good handle on it. You need to know what it is. Yeah.
But most, you can get close by looking it up, because you look at water, 0.96 to 0.98. Biological surfaces are full of water, and so they're always in 0.96 to 0.98. Like our skin is a high emissivity because it's hydrated, it's full of water. Now, sometimes it matters if it's 0.96 or it's 0.98, but biological surfaces that are full of water are always a high emissivity. But still, you can have significant errors if you don't do anything about it.
I think it's because the Moss temperature is so different from the air temperature. Even a slight difference in emissivity can drastically alter
It can.
your measurements.
Right. There's no doubt. My examples only showed, I had an example for a clear sky and a cloudy sky, but I could have just easily had an example for clear sky with an emissivity of 0.98 and clear sky with an emissivity of 0.95, and we could look at the error there. There will be an error as a function of emissivity, and so if you don't know the exact emissivity, you either have to live with that uncertainty or you have to measure the emissivity so you know what it is. Any other questions? Okay, so let's talk about field of view for a second. All right, so the actual area or the footprint that's being measured by the radiometer will depend on three things. One of them is the field of view of the radiometer. One of them is the mounting height or the distance of the radiometer from the surface that you're trying to measure. And the other one is the angle of the radiometer, whether it's looking straight down or at an angle. And so the field of view of the radiometer is defined as the angle or the half angle of the cone apex, where the cone base is the area surface being measured and the apex is right here. So just to illustrate, this particular model has a half angle field of view of 22 degrees or a full angle field of view of 44 degrees. But the best way that I like to think of field of view and the best way that I like to illustrate it is with a flashlight. And this is not necessarily a flashlight, it's just a pen with a LED on the end, but I think I can make it work for demonstration purposes. And so we're all familiar, if we go into a dark room and we hold a flashlight close to the wall and perpendicular to the wall, we get a small circle where it's pretty high intensity light, right? And then if we start moving the flashlight away from the wall, the circle gets bigger, spreads out. If we hold the pen or the flashlight next to the wall and then we start to angle it so it's no longer perpendicular to the wall, the footprint or the spot on the wall, it now spreads out into an ellipse rather than a circle. And so the field of view of a radiometer is analogous to the spot or the light dot that a flashlight makes on a wall. If your radiometer is perpendicular to the surface that you're trying to measure, it's going to have a footprint of a circle. If you're pretty close to the surface you're trying to measure, that footprint is going to be small. If you move the radiometer further from the surface, the footprint gets bigger and bigger, meaning you're averaging more and more of the ground area into the temperature measurement. Just like when we moved the flashlight away from the wall, not only did the circle get bigger, but it got less and less intense, right? So if your radiometer is perpendicular to the surface, you see a circle. As soon as you start to angle it, the footprint spreads out into an ellipse. So here are the different field of view options of infrared sensors that Apogee builds, and other companies that make infrared radiometers are likely to have different fields of view. So there's 3 of them that have a circular field of view, just different angles that make the footprint either a little bit smaller or a little bit larger. And then this one has a horizontal field of view. This one's actually designed to look at row crops. And so the field of view is wide in this dimension, but narrow in this dimension. So if you orient it horizontally like this, with row crops that are running this way, then you can try to minimize the soil that is in the field of view and maximize the plant area that's in the field of view using a horizontal field of view. So what often comes up is, that's all well and good. I understand that putting it close to the surface gives me a small footprint and moving it away from the surface gives me a big footprint, but how do I actually attach numbers to the footprint? There's a tool that you can find on the Apogee Instruments webpage that allows you to calculate in dimensions of meters squared how much land area am I going to see if I have a sensor with this field of view, for example, this height above the surface, for example, and this angle from perpendicular. So you have to know 3 numbers in order to get a footprint calculation. You have to know the field of view of the radiometer, the height above the surface that you've mounted your radiometer, and then the angle of the radiometer from perpendicular. Once you input those 3 numbers into the calculator, it will spit out meter squared of ground area that you're going to actually measure on the ground. So another question that comes up often in relation to field of view is, what do I do in this situation where I have partial canopy cover? Maybe it is row crops, or maybe it's a forest where the trees are fairly sparse. And you're trying to measure the plant canopy temperature, but you have all of this soil that you see in the background. So a couple techniques, and I won't spend too much time on these. One way that you can deal with this is angle the radiometer to try to maximize the canopy within the field of view. And so you can see if it's looking straight down, you're going to see something like, half of the area within the footprint is soil and the other half is plants. But now if you angle it, most of what you see is in the area is plants. You might still have a little sliver of soil here that you see, but by angling it you can try to get more plant area and less soil area in the footprint. So another way that you can deal with this is you can measure or estimate the soil temperature and then approximate the fractions of canopy and fraction of soil that are within the field of view. And you can use a simple equation to try to estimate the canopy temperature if you know roughly what the fraction of canopy is and the fraction of soil is and the soil temperature. So the inputs you need here are, this is the actual measured surface temperature from the sensor. This would be a measurement or estimate of the soil temperature. This one is the fraction of canopy in the field of view, and 1 minus that number is the fraction of soil within the field of view. So if you have reasonable estimates of soil temperature and then the fraction of field of view that's occupied by canopy and soil, you can try to estimate canopy temperature from the data and eliminate the soil temperature if canopy temperature is the number that you're looking for. I have a few more slides that deal with an application of infrared measurements of surface temperature, or we can take time for tea. You want to see the application? It won't take too much time. Okay, I'll try to be brief. So just a real quick summary of infrared thermometry or infrared radiometry. Small signals require a high resolution voltmeter. That's if you have an analog sensor. Nowadays a lot of sensors have analog to digital converters on board the sensor, and then they output digital signals like SDI12 or Modbus. And so if you want to make surface temperature measurements but you don't have a way to measure these small voltages, that doesn't mean you can't make the measurement. It just means you need to buy a version that outputs a digital signal like Modbus or SDI12. Emissivity correction is required. We spent quite a bit of time on that one. And remember, the radiometer averages everything within the field of view. So if you have things within the field of view that you don't want to see, you either have to reposition the sensor to eliminate them from the field of view, or if it's the case of plant canopies and soil, there's ways you can try to estimate one temperature if you know the other. I'll say, if you go to move on to the application really quick, in the past we've often made stomatal conductance measurements with these little handheld devices, or sometimes they're not little. This is a full photosynthesis system from Lycor. Some of you may be familiar with this. This is a porometer from Decagon, but they allow you to clamp on to leaves and measure stomatal conductance. And these are great instruments, but all you get is the stomatal conductance of a single leaf that you clamped on. And it also requires a person to be in the field with the instrument to make the measurement. So a few years ago, myself and Bruce and one of our colleagues set out to use infrared radiometers to try to measure plant canopy stomatal conductance automatically, basically using weather data and with the addition of an infrared measurement of the canopy temperature to estimate stomatal conductance. So I won't spend too much time here, but you're looking at a picture of the surface energy balance. So the equations over here are all the equations necessary to describe the surface energy balance. And the number that we're interested in here is the plant canopy stomatal conductance. So without going into detail, we can rearrange all of the equations that are shown here for the surface, and we can solve for this number. Everything is described in the paper on this slide, and if you're interested in the paper, I can easily send you a PDF of it. But when we do that, it gives us an equation that calculates plant canopy stomatal conductance if we have these measurements or estimates. And so we have to have the canopy temperature, air temperature, humidity, radiation, wind speed, and then some information about the height of the plants and the leaf area index. So in the previous slide I was showing a picture of one of our weather stations, and so here's where we're getting all of our weather data. And then all of these things that you see here are the infrared radiometers, and these ones are looking at a corn canopy. This was in Nebraska, I believe. So I'll just show you some data where we actually calculated stomatal conductance from the measurements that we made. So what you're looking at here is canopy stomatal conductance on the y-axis, and then x-axis says day of year. So this is day of year 195 through day of year 206. Those would be roughly mid-July, or right in the middle of the summer in the northern hemisphere. And so there's two lines on this stomatal conductance graph here, a green line and a black line. The green line is actually a model calculation of canopy stomatal conductance, and we're calling it potential conductance. And so what it is an estimate of what we expect the canopy stomatal conductance to be if the plants are well watered and not stressed. And then the black line is our actual data, the canopy stomatal conductance that we calculated from our weather measurements and our measurement of the canopy temperature from the infrared sensor. And you can see these couple days here, the black line matches the green line pretty well, indicating the plants are well watered because the calculated values of stomatal conductance are matching the modeled values. And again, the modeled values give us what we expect the theoretical value to be for well-watered conditions. And then you can see for a few days in a row, the black line is well below the green line, meaning the actual values are well under the potential values, indicating the plants are water stressed. And then over here it jumps back up again. And we have 2 or 3 days where the actual matches the potential pretty well before it starts to go down. You can see the same thing in this graph here, this is just the ratio of the two. So you take the black line divided by the green line. If we're near 1, it means the two match. If we're below 1, it means the black line is lower than the green line. So any ideas what happened right here where it jumps up? Well, you can see it declines there. Mother Nature irrigated. We got almost an inch of rainfall. The cornfield that I showed was naturally irrigated, and when the rain fell, it bumped back up like we would expect it to do. And so this is just one application that you could potentially pursue with infrared measurements. They can give you information about plant canopy water status and plant response to their environment. Here we're looking at stomatal response. One more graph. This just shows a plot of the potential value, so a reference value on this axis, and then the actual value, our calculated value, on this axis. This is from the exact same experiment in Nebraska in the United States, and it was corn. And all we're doing here is plotting the two for the days immediately after rainfall, when we expect that our actual value should match our modeled value, and indeed that's what we get. As long as the plants are well watered, the two numbers match. So it indicates that our method of getting actual is working pretty well. The outliers are possibly when the canopy was wet. Right? You'll get data that don't necessarily match the model if the leaf surfaces are wet. Yeah. That's all I have for stomatal conductance for the application. Are there any questions about any of the IR measurement details that we covered? And any questions about this specific application?